So, hi everyone, my name is Pradyumn, and today we will discuss the solutions to the CC Starters 191 contest of Division 2. Alright, and we'll solve the first 5 problems of Division 2. So, let's begin. So, the first one was add to get GCD. Okay, so the problem said that you have two numbers. Like, okay, let's just let this load. And okay, so while it is loading, I'll just explain the question. So the problem said that we have two numbers x and y. Okay, x and y, and we have to like in one move, what we can do is we can either increase x by 1 or we can increase y by 1. So in one move we can do that, right? And we need to find the minimum number of moves such that the GCD of the new value of x and y is like not equal to 1, so greater than 1, or let's say not equal to 1, right? Same thing. So we have to find the minimum number of moves, right? Okay. So here in the samples we have 2 and 4 for sample. So like in the initial value only, their GCD is not 1, like it is greater than 1, it is 2, right? So the moves is 0. Now in second test case we have 1 and 1. So if we just increase any one of them, like if I increase this one but not this one, then the GCD will be 1 only, right? So we'll increase both of them. So if we increase both of them, it will become 2 and 2, and the GCD is 2, right? So the answer is 2. And if we increase, okay, in this test case, let's say we increase this 2 by 1. Okay, first of all, the answer is not 0, because if we don't do any operations, then the answer will be like 1. The GCD is 1 initially, right? So the answer is not 0. So is the answer 1? So for one answer, we can either increase this or increase this. So if we increase this number, then it is 3 and 3, right? And the GCD is equal to 3. So it is greater than 1. So in one move, we can do it. So the answer is 1 for this, right? So we have to determine the minimum number of moves, right? So this is pretty easy. Like if you just know that the GCD, the GCD of two even numbers, if both are even, right, then it is like greater than 1, right? It is at least 2. If you take GCD of two even numbers, then of course they have a factor of 2 at least. So GCD is not 1 for them, right? So if you have initially both even numbers, yeah. So if you have initially both even numbers, then the answer is 0, of course. If you have some odd number and one even number, then the answer is like it might be 1, it might be 0 also. It is 0 when the initial numbers have a common factor, like let's say 3 and 6. So in this case, the answer is 0, right? But if their GCD is 1 initially, then you will just increase this odd number to a even number, right? And then you have two even numbers. So you will get non 1 GCD in just one move, right? And otherwise, like let's say you have two odd numbers, okay? Then in the worst case, like either the answer is 0 or it is 1 or it is 2. So let me explain that. Like let's say we have 3 and 5. Okay. So for 3 and 5, the GCD is 1, right? The GCD is 1. So the answer is not 0, not 0. But if you increase this 5 to a 1, okay, then the answer, like if you increase this 5, then it becomes 3 comma 6, right? So you can just in one move, in one move you can get this, right? So no, Aditya, that is not correct. If you have two odds, then he is saying that the answer is 2, but that is not like really true, because if you have two odds, then it might happen then the answer is 0 or 1 as well. Like if you have two odd numbers, then the answer might be 0, it might be 1, or in the worst case it is 2. Like if you just increase both of them, if you increase both of them, the answer is 2, right? But you can do better also, in some cases. Like if you have 3 and 5, then you can just increase this 5 and make it 3 and 6. So the answer is 1 for 3 and 5. So basically, what you can simply use is that the answer is at max 2. Like if you maybe basically the answer is at max 2. The answer is less than equal to 2, right? So like what you will try, that is the answer 0? First you will check that. Is the answer 0? So for that you will just take the GCD of x and y, and if that is not equal to 1, then the answer is 0, right? So if it is equal to 1, then you will check, like then you will try to increase both x and y. Okay, so you will try the GCD of x plus 1 and y, and x and y plus 1. Okay, so if any one of these are not equal to 1, then definitely the answer is 1, right? And like if it is odd and even, like let's say if x is odd and y is even, then definitely this one will give me non 1 GCD. And if my x is even and y is odd, then this will give me non 1 GCD, right? So if I have the, like these two cases, or if I have even and even, if I have even, then the answer is 0. If I have odd even or even odd, then either the answer is 0 or it will be 1 in this step, right? Otherwise I have odd and odd, right? So in that case, the answer is 2. Like, do you get me? Like basically, if we have even, or we have odd even, or we have even odd, or we have odd. So there are four cases right now, and what we can just check is that is the answer 0, or is the answer 1, or is the answer 2. So if the answer is 0, that means the GCD of x and y is not equal to 1. So you just check that. If it is not equal to 1, then you will print 0. Sorry, you will print 0. Then what you will do is you will try one operation. One operation means either x plus 1 comma y, or x comma y plus 1. So you check both of them. If any of them is not equal to 1, then you can just say that the answer is 1, right? And if both are equal to 1, then the answer is just 2. All right. So that's the entire logic here. That in the worst case also the answer is 2. So you can just see this, my code. So here you have xy, c in xy. If the GCD of x and y is greater than 1, then just print 0. Okay, otherwise, if GCD of x plus 1y is greater than 1, then print 1. Like either x plus 1y or x and y plus 1. If they are greater than 1, then just print 1, right? Otherwise, print 2. Okay, that's the entire logic here. All right. So I hope it is okay. So all the participants in this meeting, do you have any doubts? You can ask if you have any doubt. Okay, so since I am not getting any no, I will assume that there are no doubts. Okay. So next question was this one. It is called permuted greater than 2. You have an array A consisting of x zeros, y ones, and z twos. check if it is possible to rearrange this array A such that A of I plus A of I plus 1 is greater than or equal to 2 for each I from 1 to length of A minus 1. Print yes or no. Okay. So basically what we have here is that we have x zeros, then we have y ones, and we have z twos. Right. And we want to just rearrange them. We want to rearrange them in such a way that uh, your A of I plus A of I plus 1, like in your rearranged array A, your A of I plus A of I plus 1 should be at least 2 for every index I. Okay. So you have to check if you can rearrange it or not. So how do you check it? Now, first of all, one thing to notice is that if you have a zero somewhere, okay, then basically you cannot have 1 or 0 side by side to 0. Like if you have a 0 somewhere, then its neighbors, like if there are neighbors, then its neighbors have to be 2. Okay. So if there are neighbors of this 0, then they have to be a 2, right? Because they cannot be a 0 or a 1. Because in that case, this sum would not be at least 2, right? So if you have a 0 and it's not the first and last, that means it has two neighbors in your array. So they have to be 2. Like if you have formed this array, then if you have a 0 in the middle, if you have a 0 right here, then the neighbor has to be 2. Okay. So what you can just see is that whatever zeros you have, you can arrange them in this way, like 0 2, 0 2, 0 2, 0 2, and so on. Like let's say you have 4 zeros and 4 twos. Okay. Then you can arrange them like this. So every 0 has its neighbors as 2. Like this 0 has only one neighbor and it is 2, right? And this 0 has two neighbors and they are both 2. So they have to be both 2. So for that, we have to ensure that we do it like this: 0 2 0 2 0 2 0 2 0 2, right? Or we can do 2 0 2 0 if we want, like 2 0 2 0 2 0 and so on. But the thing is that every 0 has to have a neighbor as a 2. But what if we have more zeros than twos? Like let's say we have 5 zeros and only 3 twos. Okay. Then we can't do anything. Okay. Like since we want that for every 0, there has to be a 2 side by side. Like let's just assume that this is the first index and this is the last index in best case. So in that case also, we need to have at least 4 zeros, right? At least 4 zeros we need to have. But sorry, 4 twos. We need to have at least 4 twos if we have 5 zeros, so that we can do it like this. So if we have like more number of zeros than 2, then can be at least like at most x plus 1. I mean, you have z twos and you have x zeros, right? So at max, this z has to be less than equal to x plus 1. I mean, sorry, उल्टा लिख दिया, x has to be less than equal to z plus z minus 1, or sorry, z plus 1. My bad. What I am saying is that let's say you have 5 zeros. If you have 5 zeros, then for them you need at least 4 twos. Okay. And you can just rearrange them like this: 0 2 0 2 0 2 0 2 and 0. So as you can see, I have 4 twos right here and 5 zeros. But if you have less than that, then it doesn't work. So like your z has to be either equal to x minus 1, right? Or it can be greater than that. or it can be z greater than equal to x, right? But if you have, okay, now what about the ones? Like, what about the remaining twos and the ones? So, what we have done till now is that we have placed all the zeros and we have placed the two in the between. We have placed these twos in between, right? But what about the remaining elements? Like, what about the other twos and all the ones? Okay. So, what you can simply do is you can put a 2 right here and then just place all the ones. Like, okay, just place all the twos right here, all the remaining twos, and all the ones, right? Okay. So, that makes it fine. But if you have no more twos, like you had x zeros, right? You had 5 zeros. So, you placed those 5 zeros and you placed these 4 twos in between. And if you don't have any more twos with you, then what will you do? Then actually it is not possible. Like then you cannot place these ones right here because this 0 1 will get um, like not satisfied. So basically there are two cases that your number of twos is exactly same, like exactly x minus 1. If z equal to x minus 1, then you have this, but you cannot place any more ones. Like y has to be equal to 0. If you have z equal to x minus 1, then your y has to be equal to 0. Okay. And if z is greater than equal to x, then it is fine. Like, so our answer is that if z is greater than equal to x, then our answer is yes. And why is that? Because we can just place 0 2 0 2 0 2. Let's say this is done. Like number of zeros is 3. Then we can just place all the twos, 2 2 2 2, and then 1 1 1 1, and that's fine, right? But if we have z equal to x minus 1, then that means we have one less 2 than the number of zeros. So when we place this 0 2 0 2 0 2 0 2, so and 0, so like we have, let's say, 5 zeros, then we have placed all the 4 twos that we have, and now we just have ones remaining. But now what do I do with 1? I can't do anything with 1. I have to place 1 here and it will give me a conflict. So if my y is not equal to 0 in this case, then the answer is no. And if y is equal to 0, then the answer is yes, right? This is the case when z equal to x minus 1. And if z equal to x, I mean greater than equal to x, then the answer is yes, right? And if z is less than x minus 1, z is less than x minus 1, then the answer is no. Okay. All right. So this is the entire logic here. So the ones who did not solve it in the contest, do you get it now? Like any doubts, guys? Just tell me. No doubts, Aditya. Okay. Others, just let me know. Okay, I'm seeing no doubts. So we have the code right here. Int xyz, c in xyz. If z less than x minus 1, then the answer is no, right? Else if z equals to x minus 1, then if y equal to 0, then the answer is yes. Otherwise, the answer is no. And if z is greater than equal to x, then the answer is yes. All right. So it's cool. Uh, this was the problem B of division 2. And we will move on to the next one. Okay. So we have this problem, grid path easy. You have a binary grid of size 2 by n. The jth character of the ith row is aij. In one operation, you can choose a row x and a column y, and then swap axy and a of x y plus 1. That is, you are allowed to make adjacent swaps in the same row. You want to find out the minimum number of operations needed to make the grid have a write down path from 1 1 to 2n, considering only once. I mean, consisting of only once. That is, if you visit xy in your path, then a xy must be 1. If it is impossible, then print minus 1. And in this case, there are no updates. Okay. A write down path is the one which moves to either cell x plus 1y or x y plus 1 from cell xy. So the problem here says that we have to, like, we have a binary string. Okay. I mean, we have a 2 by n grid, binary grid, 2 by n size. Ke. Okay. So it has 2 rows and n columns. And in every cell, there is a written like 0 or 1. There is either 0 or 1. Right. Okay. And what we want to do is that, like, we can swap any two indices in the same row. I mean, not any two, any two adjacent. So we can swap these two, or we can swap these two, or we can swap these two, and so on. So in one move, we can do that, right? And in second row also we can do this like this, right? And what we have to ensure is that there is a path from this top left corner to the bottom right corner, such that we are only moving right and down. So we can move right and we can move down during our path, right? So it can move, it can be like this, or it can be like this, or it can be like this. But like in our paths, we can only move down and right. Okay, right? So what is the minimum number of operations that we need to do? All right, that's the problem right here. That's the problem. So for this, what you can do, like you can, okay, guys, if I ask you this thing, that let's say I want to traverse this path. Okay, like I am telling you that I want this path only. Okay, then what is the number of steps that you need? Like how many steps do you need to traverse this path? So basically, you want all four of these to be one, right? Like here one, here one, here one, and here one, and also these five also should be one. So this one, this one, this one, this one, this one. So you want all these 9 cells to be one, right? If you want this path, yeah, all 4 boxes in the first row to be one, and all 5 boxes in second row to be one. So how many steps do you need for that? So let us see about that. So if you need all four of these to be a one, and all you can do is you can swap in the same row. Like you can swap two elements in the same row. So in this case, what you will do is you will just make this one go here, like using this one swap, right? Then you will bring this one here. Then you will bring this one, sorry, this one right here, and this one right here. So basically, these four ones that you have, these four ones, you will bring it to these first four places, right? And in doing that, how many steps do you need? Like to do that, how many steps do you need? So like let's say we have an array. Basically, we have an array. Yeah, 7 in this case. I mean, is it 7 really? We'll check. So we have 0 1 0 1 1 1 0 0, and we want that all of these should come to the front. Like all four ones should come to the front. So basically, I'll just index this. Okay, I will index the positions of these. So 0 1 2 3 4 5 6 7. All right. So this one, which was initially on the first index, it has to go to 0th index, right? So it will take one move to go from here to here. Okay. Then this 3, which was there on this index, 3 index, it has to come on one index, right? So this will take two moves. Okay. Now this 4 which was there on fourth index has to be on second index right here. So that will also take 4 minus 2, which is two moves. And this one which is on the fifth index has to come to third index. So it will take 5 minus 3, right? So it is 7. That is correct. So in general, if we have an array of zeros and ones, 0 1 0 1 1 0 1 0 1, let's say, and we want the first three indices to be 1, let's say, then what we'll do is we will just look at the first three ones, this one, and this one. Okay. So their indices are what? This index is 1, this is 3, and this is 4. And you want them to be at 0, 1, and 2. So what you will just do is you will add these three values, like 1 minus 0 plus uh, 3 minus 1. Wait, my screen just blanked out. Okay, yeah. So plus 3 minus 1 plus 4 minus 2. So this is your um and like number of operations. Okay. So 2 plus 1 plus 1, 2 plus 1 plus 2, which is 5. So basically, what you have here is that you can determine that how do you have the first k indices to be 1 for any array. Like if I give you an array, let's just take this one only, then for every k, you can figure out that what is the minimum cost that you need to make the first k elements as 1. Okay, like here you have 5 ones, right? So let's say you just need the first index to be 1, then that would need one operation, right? So let's say basically if you need all the indices from 0 to 0 to be 1, then that will take um, one move, right? So I am making this new array. Okay, I am making this new array which will contain that if I want to make, like, let's say this is ARR, or let's say this is pre array. So pre of I, pre of I is storing that if I want all the elements from 0 to I to be 1, then how many minimum moves do I need? Okay. So pre of 0 is 1. Why? Because the first one is at the index 1 and we need at the index 0. Alright, so it is 1. Then what about pre of 2? I mean pre of 1. So we want a 1 here as well. So that is basically the cost of moving the ones. Like basically it is pre of I minus 1. This pre of I is just pre of I minus 1 plus this index right here. So like the number of moves to make the second one come to index 1. So since the second one is index 3 initially, so it will take two moves. So pre of 1 will become 3, right? Then similarly, pre of 2 will become what? Pre of 2 will become 3 plus the number of moves to bring this 1 to index 2. That is 4 minus 2. So 3 plus 2, which is 5. Okay. Then pre of 3, similarly, it will be this index is 5, this is 6, this is 7, this is 8, right? So pre of 3 will be what will you need? 6 minus 3. So 5 plus 3, which is 8, right? Like you want to bring this one at index 6 to index number 3. So you need 3 moves to do that, and plus this 5. So you have 8. And similarly, for pre of 4, pre of 4 will be 8 plus 4. This 8 minus 4 is 4. So 4 plus 8, which is 12. Okay. And the rest of them you cannot fill. Like you cannot have the first 6, that means 0 to 5 as 1. Like in this array, you cannot have the indices from 0 to 5 as 1 because you have only 5 ones. So at max, you can make only from 0 to 4 as 1, right? So in the rest of them, I'll store minus 1. Okay. So that's how you will find the pre-array. Where pre-array means that pre of I is the minimum cost to ensure that all my elements from 0 to I have 1 in it, right? For the first row, I mean, right? Like if you want to go from here to here, then in the first row, you need that from 0 to 3, you need um, your all to be 1, right? And in second row, you need from 3 to n minus 1 to be 1, all to be 1, right? So just like you calculated this pre-array for this first row, like you just found out this pre-array for the first row, you can find out the post array for second row. Where what is the post of I? Like what is post array? Post array means like post of I means that you need all the indices from I to n minus 1 to be equal to 1. Okay. So just like you calculated pre of I using pre of I minus 1, you will calculate this post of I using post of I plus 1, right? So I'll just tell you how to do that. Like I'll just show you. So let's say you have this 0 1 0 1 1 0 1 0 1, right? So if you want to make the post array, okay. So what is the post array? So post of I, like here the indices are what? 0 1 2 3 4 5 6 7 8, right? 8 7 6 5 4 3 2 1 0. Yeah. So what is post of 8? Post of 8 means that how many operations do I need to ensure that all the indices from 8 to 8 should be 1. So it is already 1, right? So the answer is 0. I need no moves to do that. Then what about post of 7? Post of 7 is basically that I need all from 7 to 8 to be there on this, like these to be 1, right? So I will have to do these two. So basically second last one, I need to bring it to position number 7, and it is at 6, right? So the cost is 7 minus 6, which is 1. So I'll add this 0 to 1. Satya, we're discussing this problem, which was grid path easy. Okay. So yeah, post of 7 is 1. Then we have post of 6. That means we need all elements from 6 to 8 to be 1. So third last one is at index 4, and we want to move to index 6, right? So index 6, that means we need 2 cost. So 1 plus 2, which is 3. And similarly, you can just make the entire post array. All right. So basically, you have now 2 arrays, your post of I and your pre of I. So post of I stores that from I to n minus 1. If you want all indices to be equal to 1, then what's your minimum cost? And pre of I stores that if all the indices from 0 to I, if you want to be 1, then what's the minimum cost? So what you can just do, like what you can simply do is you iterate over all the paths. Like see, um, if in this grid, you want to go from this top left to the bottom right, correct? And you can only move down and right. So that means that you will move down at some index. Like either you can do this, or you can do something like this, or you can do this, or you can do this, and so on. Look, so the path will look like this: that you will first move somewhat right, then you will go one step down, and then again you will go these steps right. So you can just iterate over the position where you are going down. Like either you can go down from this index like this, or you can go down from this index like this. So you can just iterate over all the different positions from which you can go down, right? And let's say you want to go down at the index I, like this is the index I, and you want to go down from the index I, okay, like this. Then what you will do, like what's your cost? your cost is just pre of I plus post of I. Okay. Why? Because if you're going down at the index I, that means you need the 0 to I indices to be 1, and you also need the I to n minus 1 indices to be 1 in this second row, right? So it is pre of I plus post of I, assuming that they are not minus 1. Like if they are minus 1, then you will just ignore them. Like you cannot go down at this index, right? So if they are not minus 1, then the answer is pre I plus post I. So you will just iterate over all I, like just check for all I, and just see that what is the minimum answer that you are getting for which I, and like what is the minimum answer. So you just print that minimum answer that you have got. Okay. So is it fine, guys? The logic, just let me know. Okay. What about the others? Okay. So I'll just show the code now. So here I have n comma q, c and n comma q. Like in the input they have given q as well, but q is 0 always. But I have taken it in the variable. Then I'll take the input of the string. Like I have this array of strings of length 2 basically. So I have one string for top row and one string for bottom row, and I'll see in s of I. Then I have vector of int pre of n min. Like I have two vectors pre and post. All right. And then what I did was I just stored all the positions of the ones. Like what I just did was that in pos of I, like I have a vector called pos. I mean I have two vectors called pos. Basically for the top row and the bottom row. Like for the top row and for the bottom row, I have two vectors, both named pos. Okay. And the pos of I stores the position of the ith one. The ith one. Okay. So what I'm doing here is that for both the rows, for int I equal to 0, I less than to I plus plus, and iterate over the entire 0 to n minus 1. If s of I comma j is equal to 1, then pos dot pushback j. Pos for the that row, pos of I dot pushback j. So that is the jth, sorry, this current thing is the index j. So I'll push back the index j into my positions array. So this positions array just stores the positions of all the ones in my string, right? And if any one of them is 0, that means if there is no 1 in any one of them, then I'll print -1, because I definitely need at least one, at least a single one in both the rows, right? In fact, I need that their like the total number of ones should be at least n plus 1, right? But anyways, I that will happen in this loop only. So okay, now I just make the pre and the post arrays. So pre of 0 is basically pos of 0 comma 0 minus 0. That means where is the first one in my top row? Minus 0, because I want to bring it to 0, right? Then for int I equal to 1, I less than pos of 0 dot size I plus plus pre of I equals to pre of I minus 1 plus pos of 0 comma I, that is the ith one ka position, minus I. Like I want to bring it from pos of 0 comma I to I. So I'll take this much cost, additional cost, right? And similarly, I'll do for post of n minus 1. So post n minus 1 equal to n minus 1 minus pos of 1 dot back. And like pos 1 dot back means the last one. Wherever it is, I'll just bring it to n minus 1. And to do that, I'll take these many number of steps, right? Then from n minus 2 to 0, like basically I'm just iterating over all the ones. So for I equal to n minus 2, j equal to pos of 1 dot size minus 2. So I'll start from the back, and like since I have like already used the last one, I'm starting from second last one, right? It is second last one, and j greater than equal to 0, I minus minus j minus minus. So post of I equal to post of I plus 1 plus 1 minus pos of 1 comma j. So currently my jth one is at pos of 1 comma j, and I want it at I, right? So this much move I'll take, and finally I'll just take ans equals to min of ans comma pre I plus post I, right? For all I, I'll check that, and finally if my ans is not equal to long max, so like if it got initialized, then I'll print ans. Otherwise, I'll print -1. And like this -1 will come if you have less than n plus 1 zeros. I mean, n plus 1 ones. I mean, okay. Otherwise, the answer is something non -1. Okay, so we have a doubt. Why couldn't we think in the direction of DP here? That should I bring a 1 to that position or change the row? Um, well, maybe that could work. Like your state would just be that whether you are in top or in the bottom and your index. So you will have 2 into n states. I mean, that could work, yeah. But to transition, you will also need that where are the one's positions. Like to determine that should you bring a 1 to that position or change the row. For that, you will need to have that what is the cost of bringing a 1 to that position, right? So yeah, you can use DP. That is fine. Like that is also correct. Okay. So yeah, we will move on to the next one. So we have here add 1 or 2. Okay. So you are given an array A of size n, A1 to AN. There will be B1 plus B2 plus up to Bn total events with exactly BI events of type I. The type I events will happen before type I plus 1 events for each I from 1 to n. In an event of type X, you must do one of the following: add A1 to X, sorry, add 1 to AX, or add 2 to AY for any Y not equal to X. Okay, so you have two options. Like for in the event of type X, either you can add 1 to AX or you can add 2 to any AY which is not equal to X for any Y not equal to X. Note that the choice is made independently for each event. Okay. After all the events are done, you want to minimize the maximum value from A1 to AN. Find this minima value. Okay. So yeah, what we have here is that just 1 minute. Yeah, so we have been given an array A from A1 to AN. Okay. And also we have been given one more array B from B1 up to Bn, right? And we will first do the event of type 1 B1 times. So basically the event of type 1 will happen B1 times, then B2 times, the event of type 2 will happen, and so on, right? And in the event of type X, like in type X event, what you can do is either you can increase AX by 1, okay, or you can increase some ay by 2, any ay by 2. All right. And finally, what you have to do is that you have to minimize the final maximum value of the array. Okay. So like here, for example, they have given 3, 5 and 1, 2. Okay. So we have 3, 5 and 1, 2. So that means we do the event of type 1 once and the event of type 2 twice. Okay. So first we'll do the event of type 1. That means either we can add 1 to this one or we can add 2 to this one, right? So we will just add 1 to this one. So the array will become 4, comma 5. Okay. Now we have done one type 1 one. So we have to do two type 2 ones, type 2s, right? So here what we can just do is we can like either add 2, add 2 to this one or add 1 to this one. Okay, so we'll just add 1 to this. So 4, comma 6, right? And again, we want to do a type 2 operation. So type 2 means either we can add 1 to here or 2 to here. So we'll add 2 to here. So it will become 6, comma 6. Okay, 6, comma 6 it will become. And the maximum value is equal to 6. All right. So the answer is 6. And like you cannot have the maximum value less than 6 in any way. Okay. So like if you try to make the maximum value as 5, then it is not possible. All right. So yeah, that's the problem. And what we can do to solve this is we can first of all, okay, just notice this one thing, that we want to minimize the maximum. So that sounds like binary search, right? I mean, if you have done many BS problems, so to minimize the maximum, you often use binary search on the answer. Okay. So what you will do is basically you will do a BS on the answer. And like simply what you are doing is for some k, like if your mid value is equal to k, then you are simply checking that can you make the maximum value less than equal to k, right? So if you know that how to check that can we make the maximum value less than equal to k, then we can just do a BS on this k. All right. And let's say the answer is 5. Like if the answer is 5, that we can make the maximum value at least 5. Okay. Then in that case, when we do a check for 4, it will give us false, right? That means if we check that can we make the maximum value less than equal to 4, it will give false, right? And if we check for 5, it will give true. That means we can make the maximum value less than equal to 5. So basically our check function is monotonic. Like up till 4 it will give false. Okay. False, 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 false. 0, 1, 2, 3, 4. It is false. And from 5 it is true. So we can just perform a based on the answer like this. That in our check function, we will check that can we make the maximum value less than equal to k. That means can we make all the values all the values less than equal to k, right? If we want the maximum value less than equal to k in our array, then that means all values in the array have to be less than equal to k. That's the same thing, right? So basically in our array from a1 to an, a1, a2 up to an, we have that we need to make all the values less than equal to k, right? So can we do that? So for now, like let's just try on samples so that you can maybe understand a little bit better. So let's say we have 1 to 1 and 2 1 1. 1 to 1 and 2 1 1. Right. So basically you want to perform two operations of the first type, one of second type, one of third type. Right. And let's say you're checking for 4. Like let's say you are doing a check for 4. That means that you need to ensure that every number in your array is less than equal to 4. Okay. So all right. Now this one is pretty simple actually, because you can simply add them here. Like when you're doing the type x operation, like when you're doing type 1 operation, just add 1 to this one. Yeah, so this is pretty easy. Like basically you will just add 1 for all of these, so you will get the array as 3 3 and 2. Okay. So less than equal to 4 is possible, right? But let's take the fifth test case. Yeah, right. Okay. Fifth test case is what? 1 2 3 4 5. So we have 2 2 5 4 and 3 3 1 3. All right. So we want that. Okay. So let's check for 7. Okay. We know the answer is 7. So let's check for 7. All right. So let's check for 7. Okay. So in this case, basically you want that your numbers should not be exceeding 7. Okay. So okay. Now initially your A1 is 2. Okay. And you want to perform the type of option 3 times. You want to do type 1 3 times. All right. So if you just add 1 to this index, then it becomes 5. All right. Okay. Then again, same thing you will do here for all type 2 operations. You will add 1 to A2. So it becomes 5. Then for this type of operation, you can just add 1 to 5, so it becomes 6. And for this one, you can add 3 to 4, so it becomes 7. So in this case, check of 7 returns true. Okay. So this is also not very interesting. What we could have taken is, let's take here 4 4 1 3. Like let's take, or not 4 4. Let's just take 3 3 1 5. Okay. Like 2 2 5 4 and 3 3 1 5. Okay. And let's check for 7. Let's check for 7. So what we can do is, here if we just add 1 for all three operations, we will just get 5, and 5 is allowed, so we'll add 5. Then for type 2 also we'll just add 1, so we'll get 5. Then for type 3 we'll add 1, so we'll get 6. And now adding this 5 to 4, we will get 9, and that's not allowed. That's not allowed. So basically we cannot really add, like, so we want to do 5 type 4 operations, right? Type 4 operations, but we can only add to this 4 3 times, like only 3 times. 3 times a of 4 plus plus, we can do that, so it becomes 7, right? And now we are left with 2 operations left. Okay. So what do you do with those 2 operations? You can just apply them to these 2 indices. Like one operation you can apply here, like just add 2. Okay. And one of them apply here, just add 2. So you have also done this 5 type 4 operations, and your array becomes 7 7 6 7. Okay, and therefore seven your check for 7 returns true. Okay, so basically my algorithm here is that wherever you are able to do add one, like wherever you are able to add one to your AI, okay, then just add one to that. All right, and if you cannot do that, if you cannot add one, then just add two to some indices where you have extra space. So is that algorithm clear? Like, do you understand why it is correct? Like my algorithm is my greedy algorithm, my GRAADY greedy algorithm is that as long as you can add one to the current index, do that, right? And for the rest, for the rest, just add it to, like just add to where there is space, where there is space for two. Okay. So is this greedy algo clear? Like why it is correct? Or do you have some doubts regarding this? Like why are you trying to add one first and then two? So like, do you have this doubt that why are we adding one? Like why are we trying to add one? Intuitively, is it correct to you? Okay. So yeah. So that's my algorithm. That as long as you can add one to the current index, then add one. And if you cannot add enough operations, like if your operations exceeds the gap, like here as you saw that you had only three gap, like your 7 minus 4 is 3, so you had only three gap, but you had five operations, so you have two operations left. So in that case you can just add those to the other numbers which have some gap, right? So how do you implement this? Like to implement this you can just maintain two variables. So I just maintained two variables, c1 and c2. Okay, so c1 means that how many operations are left after adding one, after adding one to an entire array. Like what I mean by that is, for example, if you have here this array 3, 1, 5 and 7, and let's say you are doing check for 8. Okay, and your B array is let's say we have 1, then let's say we have 3 or 5, let's say, then we have 4, and then we have uh 7. Okay, or let's say a 5. All right, so here I'm maintaining two variables, c1 and c2, where what is c1? C1 is that how many operations are left to do after adding one. Like here, as you can see, I can just do this one. Like I just add 1 to 3, so it becomes 4, right? So it becomes 4, and this one is done, right? And then I can add this 5, it becomes 6, right? Then for this one I cannot add this 4. I can't add this 4, right? But I can add like 3. So I'll just add 3 and make it 8. and 1 is remaining. 1 is remaining right here, and in here I can add 1, right? I can add 1, so 4 is remaining, and this becomes 8, right? So in this case, my C1 is equal to 5. My C1 is 5. Okay, correct. Now, what is C2? C2 is my, like, C2 is defined as the number of spaces, essentially. Like, basically, the number of operations, or you can say the total number of operations that that can be done in the array. Like, as you can see here, I have added 1. I have added 1 to all of them, but still I have this 1 operation left and these 4 operation left. So I have total 5 operations left, which is C1. And also I have this space left right here, right? Like, I was checking for 8, but I have this space left here because they are not yet 8. So since this is just 4, I can add 2 twice. Like, here I I can make it up to 8, right? So I can add 2 twice, and to this I can add a 2 once, right? I can add a 2 once. So basically my C2 is 3. My C2 is 3. Why? Because I can do 3 operations more in my array. Okay. And since here my C1 is greater than C2, that is, the operations left to do are greater than operations that I can do more. So basically I don't have enough space to do, right? So in that case, the answer is no. Like, it will return false. And if C1 is less than equal to C2, then it is true. Okay. So that's the entire algorithm here. So let's say I just try to check for 6 right here. Like, let's say I have this test case and I check for 6. Okay. So I have uh, 2, 2, 5, 4, and 3, 3, 1, 3. Okay. So in this case, let's say we check for 6. So first of all, I can just add all of these threes to this 2. Okay. So it becomes 5 and this one becomes 0. Then I can add all of these 3 to this 2 also. So it becomes 5 and this becomes 0. Then I can add a 1 to this. So it becomes 6 and this becomes 0. And here I cannot add all these threes because the limit is 6. So I'll add 2 and 1 is remaining, right? So here this C1 is equal to 1. Okay. But what about C2? So my C2 is equal to 0 actually, because for this index, how much gap is there? Like, 6 minus 5, only one gap is there. So 1 by 2 is 0. Like, I basically cannot add any more 2's. So if there is d amount of gap, then I can add d by 2 GIF more zeros. I mean, more 2's. If I have this much gap left, then d by 2 more 2 I can add, right? So at this index I have no space. At this index also I have no space, and here also I have no space, right? So here my C2 is equal to 0. And since here also this C1 is greater than C2, you have false. So for this test case, 6 is false and 7 is true. So 7 is the answer. Okay. So do you get this? How do I implement this? Like, how I implemented this? If you have the values of AI and BI, then it is pretty easy. AI, BI, and your mid. Okay. So if you have AI and BI, then you will just have two cases, that if you add all of these BIs into AI, then does it exceed mid or not? Like, is it less than equal to mid or is it greater than mid? and according to that you can just adjust your C1 and C2. Okay, so everyone, I think it should be clear. So just let me know if any doubts are there. Okay, I'll just show the code. I'll just show the code, and if you have any doubts in that, just let me know. All right, so I have int n, c in n, input the array A, input the array B. Low equal to 0 and high equals to 2e9. So you can see that for the given constraints, the um, highest value that can go is 2e9 for this test case only. Yes, Aditya, that's correct. Because in the C1 we have those which do not fit. Okay, like in our C1 counter, we have those for which your AI plus BI is greater than mid, right? And in C2 we have those in which AI plus BI is less than mid. So we basically have, like, in C1 we will do C1 plus equals to uh, AI plus BI minus mid if it is positive, and if it is negative, then we'll do C2 plus equals to mid minus AI plus BI divided by 2 and floor. So in C1, uh, there are those indices in which AI plus BI minus mid is positive, and in C2, those indices in which it is negative. So they are all different indices. Okay. So yeah, we have the code. Uh, okay. So int n, c in n, input the arrays A and B, low equal to 0, high equal to 2e9. While low is less than high, mid equals to low plus high by 2. If check mid, that means if it is true, then my high equal to mid, and if it is false, then I have to try a higher value. So low equal to mid plus 1. And my check function, I have, first of all, if the maximum element, I mean, if any element of the array is greater than mid, then of course return false. Like, you don't need this statement, but I just added it for my simplicity. Then C1 and C2. If AI plus BI is greater than mid, then C2 plus equals to BI um, AI plus BI minus mid. Actually, in this code, I have reversed C1 and C2. My bad. But yeah, um, you can just assume that C2 was the one which was extra. Okay. So C2 plus equals to AI plus BI, AI plus BI minus mid, right? And C1 plus equals to, like, if it is negative, then C1 plus equals to mid minus AI plus BI by 2, right? And we'll return C2 less than equal to C1. C2 less than equal to C1. All right. Okay. So this was the code. And if you have any doubts, then you can ask me. If any one of you have any doubts, just ask in the chat right now. I'll wait for 1 minute and then we'll continue. Okay, so C1 is basically, like, just see this test case. Okay. Uh I have, okay, I'll just write it again. I have 2254, right? 2254, and I have 33, or actually not this one. Let's just take another one. What was this one? Uh, I think it was 3. Mm, okay, 3, 1, 5, and 7, I guess. 3, 1, 5, 7, and okay, 3, 1, 5, 7. And what was the B array? B array was basically 2, I think. No, not sorry. B array was 1, 5, 4, I guess. Right. 1, 5, 4, and 5. 1, 5, 4, 5. Yeah, so just assume that this is test case and we are checking for 8. Okay. So my C1, actually in my code, if you can see, in my code, the C2 is that in my code, C2 is that how many extra operations are there? How many operations are left to do? Okay. So as you can see that in this case, like if I just add 1, like if I just use this 1 to add 1 in this, okay, so it becomes 4. And if I add this 5 to add here, it becomes 6. And if I add this 4 to a 5, then I can't do that because it becomes more than 8. Right? So I can add 3. So it becomes 8, and what is left is 1, right? And I can add just 1 to this, so it becomes 8 and 4 is left, right? So this 1 is left of type 3 and 4 are left of type 4. So in total, we have 5 left operations. So my C2 is equal to 5 in this case, right? And my C1 is that how many operations do I like can I perform extra? Basically, how much space do I have? Like here you can see that currently my A1 and A2 are 4 and 6, right? And they can be up to 8. Up to 8 they can be, right? So basically here we have 4 gap and here we have 2 gap. So in 4 gap we can add 2 twice, and in this 2 gap we can add 2 once. So basically we can add 2 total 3 more times in these two indices. So my C1 is 3. So C1 is just how many times more can I add? 2. How many times? How many more times can I add 2? Okay. So this was your C1 and C2. All right. So I hope it is clear to everyone now. So I will move on to the last problem of today, which was colored array. Okay. So what we have here is an array A consisting of 2 n elements is said to be good if it satisfies the following properties. All the elements are between 1 to n. A of 2i minus 1 is equal to A of 2i, and A of 2i is not equal to A of 2j for any I less than j. So essentially what they are saying is that any array of length 2n, like let's say n equal to 4, let's say, then length is 2n, which is 8. Okay, so basically they are saying that these two have to be equal. Uh, they have to be equal. Then these two also have to be equal. These also have to be equal, and these two also have to be equal, right? And also these individual groups, like these groups, cannot be same. Like you cannot have 1 1 here and also 1 1 here. Okay, so this is your entire thing. So any array of this type is called good, like 1 1 3 3 4 4 2 2. So this is called good array. Okay. Now you have been given an array A. which may not be good. You want to find out the minimum distance to some good array B. Okay. So basically, the distance between two arrays is the number of indices I, such that Ci is not less than Ci is not equal to Di. Like basically, if you have been given some array, right, you have to find out the minimum distance to any good array. Or in other words, what you need is that you need to change, like you need to change some elements to any other number so that you do the minimum changes. Like let's say you have 1 2 1 2 1 2, right? You have 1 2 1 2 and 1 2. Okay. So you want to make this a good array, and you want the minimum changes essentially, right? So what you can do is, let's say you change this 2 to a 1. So 1 1 1 2 1 2, right? Then let's say you change this to a 2. So 1 1 2 2 and 1 2. And then you change these two to a 3. So basically 1 1 2 2 3 3, right? So in this entire process, you did four operations, like one here, and two here. So you did four operations, and this is your entire solution, right? 1 1 2 2 3 3. Okay. So here the answer is 4. All right. So the problem is pretty clear now, I think, that you have an array of length 2n, right? And you want to make sure that every pair of adjacent elements is equal. Okay. And each pair, like each number, must not be more than twice, right? And you need to do the minimum number of changes to ensure this. All right. So the first thing that we can notice is that, okay, let's see, like let's say that we have a 3 and a 3 here. Okay. Like if there's some index, if there is some index on which we already have a pair like this, okay, then it is pretty sure, like then of course we will not change that. Like since we want it to be a pair and it is already a pair, so of course we don't want to change it. So we will not change it. Like we will just keep it 3 comma 3, unless here also, like unless this 3 comma 3 appears more than once. Okay. So in that case, we will just change one of them. Like we will keep one of them, and uh, this we don't care about. Okay. So basically, to sort this 3, like to make the 3, you will need 0 operations. See, if you have n equal to 5 right here, right? You have n equals to 5 right here. So you need to ensure that all of the numbers from 1, 2, 3, 4, 5, they are present, right? And they are in pair, side by side. So the number of swaps or the number of changes that you need to make to ensure that 3 is there in your array, that is 0. All right. Because this 3 is already in a pair in your array. Okay. So that is fine, right? So if you have this 3 as a pair, then definitely you will not change it, and you can just disregard these 3, like these 2, because you will definitely change them. You will definitely change them from this position. So you can just say that these are empty cells which you will change in the future. All right. So in the input, let's say you have been given, what you will just do is that for every number, if it is in a pair, then you will just ignore that. Just ignore that pair and just move on with your life. Like here, if you can see, 2 2 1 1 3 3. So here these two are in a pair. So just ignore them. These two are in a pair, so ignore them. And these are in a pair, so ignore them. Like they're already sorted. I mean, they're already done, right? So here, what is left? Nothing is left. So the answer is 0. So I'll take a better example. Like, let's say you have a 1 1, then a 1 2, then a 3 2, and a 3 4. Okay. So in this case, let's say this is your input. Here n equal to 4, and this is your input. So as you can see that here, these are the pairs in originally, right? So as you can see that here 1 1 is already there. Okay. So you will simply not change that. All right. You will simply not change that. And you have made 1 1, like you have ensured that 1 is there. Okay. And now what is left is this 1 2, this 3 2, and this 3 4. Okay. Now one more thing is pretty obvious, that let's say in this blank there is this 1 and there is this 2. And if one of them, like, see, this 1 is already used up, right? So definitely you won't keep 1 here. You won't keep a 1 here. So you will keep a 2 here. Like, my point is that you will keep a 2 here and not some other number. Why? Because let's say if you try to keep a 3 in this place, then it will take you 2 changes. Like, you will have to change this to a 3 and also this to a 3, right? It will take you 2 changes. But if you just keep 2, if you keep 2 on this index, then it will just take you 1 change, right? And since you already have these two ones right here, then definitely you will keep a 2 only on this, because 1 is done already. So you'll keep a 2 on this. So now 2 is done with 1 operation. Then in these two, this 2 is done, right? So you will change this 2 to a 3, because there is a 3 already here. So in 1 operation, you have made this 3 as well. And this 3 is also done. So you will change this index to a 4. And as you can see that the 4 is also done in 1 operation. So in this case, the answer comes out to be 3. Okay. So essentially, what you actually have here is that for every block, you can just make a choice. Okay. Like, essentially, you can see here that for this block, like for this block, and for this block, you have two choices. Like, either you will take 1 or 2, 1 and 2 in this. I mean, sorry, for this block, either you will take 1 or you will take 2. Then for this block, either you will take 3 or you will take 2. And for this block, either you will take 3 or you will take 4. Right? So you have two options for each block. And for this block, you are sure that you will take 1 only. Right? So now, so like, how do you actually determine? Like, here it was obvious, right? It was obvious here that if you take this 1 1, then obviously 1 is done here, so you won't take this 1, so you will take this 2. Then here 3 2 is there, but 2 is done, so you will take the 3. But what if it is not obvious? Like, what if it is not obvious that which one should we take? Okay, so it is pretty tough to determine that. And for that, actually, what I did in my method was I tried to convert it into a graph. Okay, and why I did that was because I had solved many problems like this where you have two choices, and that you can model using a graph. Like, actually, I have solved at least 4 problems like this, where you have to make uh, where, like, you have two options and you need to pick one. Okay, and that is solved by a graph. So, like, I have done those problems. So in this one also, I tried thinking of a graph. Okay, so what I did here was that, okay, for every pair I made one edge. Like, I make n edges, one for every pair. So there is one edge for this one edge for this one for this, and one for this. So basically what I'm doing is I'm making of n nodes, like 1 2 3 and 4. Okay, and for every pair which I have, I'll make an edge between that. So I'll make this self loop right here. Then between 1 and 2, I'll make this edge, right? And The edges are not directed, they're undirected. Okay. Then for 3 2, I'll make this edge, and for this 3 4, I'll make this edge. All right. So now what is our goal? Our main goal is that I need to give every edge a number, right? Essentially, I have 1 1 here, right? I have 1 1 here, I have 1 2 here, I have 3 2 here, and I have 3 4 here. So I need to give every edge a number. Like, let's say this edge is there. So it is 1 1. So I give this edge number 1. Then let's say I give this edge number 2, this edge number 3, and this is number 4. So this corresponds to that I am putting these two 4 for this edge. Then for this edge, I am putting these two as 3s. And for this edge, I am putting these two as 2s. And for this one, I am putting these two as 1s. Right? And what we would prefer is that whatever number we give, like whatever number we give to this edge, that should be one of its neighbors. Okay. Like let's say that to this edge, I give 3. Okay. That means I am trying to put 3 and 3 right here. Right. So in that case, it will cost me 2 coins essentially. Like I have to make 2 changes, right? I'll have to make 2 changes. So that is not optimal. So what I'll try to do is I'll try to ensure that whatever number I give to my edges, it is either one of these two. So that will minimize my cost. Okay. So basically, I will try to give every edge a number such that every number that I give is one of the nodes that the edge joins. Like this edge joins 1 and 2. So I'll try that either this edge is 1 or it is 2. And also I have to ensure that every number is written only once. Like I cannot really give this 1. Like I have given this edge to a 1. So I can't really give this edge a 1 because in that case I'll have 1 twice. Okay. So actually what you can do, like actually what you can say is that you want to direct, like you want to direct every edge. Basically, currently these are undirected, right? Edges. So you want to direct every edge such that every node has in degree 1. Like here, if I direct this edge like this, so now this one has an in degree of 1. If I direct this edge like this, and this edge like this, and this edge like this, so here as you can see in this graph, every node has a degree, like an in degree of 1. So basically directing it like this essentially means that I am writing a number 2 on here, which means that I am like doing this, right? Okay, so do you get this? Do you get till here, guys? That what is my analogy? That I am making a graph for the vertices 1 to n, and I'm adding the edges between those vertices which are in the pair in my array. Okay, so I have n edges. So do you get this part till here? Like what my aim is that I want to number every edge and write a number on every edge such that on each edge I will try in the optimal case that the number which is written is one of these two, right? So essentially I am just trying to direct these edges, right? Okay, so now let's see that how to do that. Okay, so I'll take some graphs in front of you, and yeah, first of all, one more thing to notice is that let's say you have a self loop. Okay, then in that case the cost is 0. Okay, so for self loop the cost is 0 because if it is already 1 1, and you are giving it 1 1, then you are not changing anything, right? Then if you direct an edge, it will take cost 1. That means if you give the number, like if you give an edge a number which is either one of its endpoints, like if you give this edge either 1 or 2, okay, then the cost is 1, because in that case you will change only one of the numbers in that pair, right? And if you give the edge a different number, then the cost would be 2. The cost is 2 if you just give the edge a different number, because in that case you will need to change both the numbers, right? Like if you give this edge the number 3, that means you need 3 here, so you will need to change both of these numbers, so cost is 2. Okay, so yeah, now I'll just take some examples. I'll take some examples and just show you how to direct this. Like let's say I have a graph like this. Okay, so I have a graph like this which has this one cycle, right? And all the other nodes are form of trees. Like this is one tree on this cycle, and this is also another tree on this cycle. So if I have this type of graph, then what I can do is I can just direct it like this. Like cycle ko just make it clockwise. Okay. So if I just direct the cycle like this, and now the other nodes, I make it like this. Okay. So if you have a cycle like this, then what you will just do is that for the cycle, you will just make it clockwise. And for the rest of the nodes, you will direct the edges away from the cycle. Like if a cycle is here, so you are directing the edges downward. Okay. So in this figure, you can see that every node has an in degree of 1, and every edge has been directed like this, right? So basically, to ensure that all of these nodes have been there in the array, like see, what does this graph means? Like what does this graph mean? I'll explain a bit more. Like let's say I have a graph like this, 1 2 3, and then let's say 4 5 and 6. So this graph has come from this array. What array? This array. 1 2 1 3 2 3 4 5 4 6 and 2 4. So if this is your array, then your graph looks like this, right? And in this case, what you will just do is you will direct the edges like this, clockwise in the graph and away from the cycle in your tree. Okay. So that means that for this 1 2 edge, like for this edge, you are choosing 2. Like you are keeping here 2 and 2. So this will take only one cost, right? Then for this 1 3 edge, you are choosing 1, right? And for this 2 3 edge, you are choosing the 3. So all these two also will take 1 1 steps each. And then for this 2 4, you are choosing 4, right? So it will take one step each. And for this 4 6 and 5 6, sorry, 4 5, you are choosing 5 and 6. So 5 5 here and 6 6 here. So that will take 1 1 point each. So you will have 6 cost for this. So if your graph is like this, then you can direct the edges such that it will take only 6 coins to do this, right? And that's optimal. But what if in your graph you don't have a cycle? Okay. Like if in your graph you have at least one cycle, then you can simply do this. And that's how you can direct all the nodes. Like for all the nodes, you will have 1 in degree, right? But what if you don't have a cycle in your graph? Like, let's say you have a tree like structure. Okay. Like, for example, if you have 1, 2, 3, and 4, and you have 5, 6, and let's say you have a self loop here and self loop here. Okay. So your array looks like this. 1, 2, 1, 4, 2, 3, then 5, 5, then 6, 6, and 5, 6, right? So here you can see you have a cycle, right? In fact, you have self loop as well. So you'll just give self loop. So you will just direct this to a 5 and direct this to a 6. So 5, 5 here and 6, 6 here. Okay. And here you have a tree. So if you have a tree, then like basically in a tree, that means if you have n nodes in your tree, then you have only n minus 1 edges, right? So even if you direct all the edges somehow, then also one node will be remaining, right? So like if you try to direct it like this, that this edge is pointing towards 2, pointing towards 3, and pointing towards 4, then this 1 is remaining. Okay. So in that case, making this 2 would take just one step, because this 1, 2 edge points towards 2. So making this 2 takes one step. Then this 2, 3, 2, 3 is pointing towards 3, so it takes one step, right? And this 1, 4, this also takes one step, right? But to make this 1, to make this 1, we will need to use an extra edge, like this edge right from right here. So for that, we will need to make two changes. We'll need to make two changes, right? So as you can see in this case, if you have a tree, okay, then the total cost for that tree is actually n plus 1. Like if you have this 4 vertex tree, right? So for a 4 vertices tree, for these 3 vertices, the cost is 1, because you can just direct the edge and the cost will become 1. And for this vertex, the cost will be 2, because you are not directing any edges right here. So you have to replace an entire edge to make it 1. So you will have the cost of 2. So the final cost is 5 for this tree, right? And for this graph, since you have two self loops, right? So in that case, you don't need any like cost. So the cost is 0 for self loops, right? But in general, if you don't have self loops, like if you don't have any self loops, I mean, if you have a graph like this, if you just have a graph like this with no self loops, but a cycle, right? So if you have a cycle, then the answer is 6. Like if you have a n size ka graph and you have at least one cycle, then you can simply orient the edges like this and get the answer as n. Okay. So if a component has a cycle, then the answer is n. And if it doesn't, that is, it's a tree. Okay. Then the answer is n plus 1 for that tree. But you just need to subtract the number of self loops. Like here you can see that even though this is a graph, right? This is a graph with cycles. Like this is a cycle, okay? So this is a graph with cycles. So ideally its cost should be 2, right? But here we have two self loop also. So we will subtract 2 and the cost is 0. So your final answer is just like what you will just do is for every component in your graph, for each component, um, if it is a tree, if it is a tree, then the cost is n plus 1. And if it is having a cycle, if it is having a cycle, then the answer is n. The cost for that is n. And you have to subtract the number of self loops, number of elements having a self loop. Okay. So this is the approach which you can take. And so yeah, and like to implement this, you can just use DSU, where like in DSU you store, right? You store that what is the parent, who is the parent of the current node, and the size of the component, size of the current component. But you can also store in the DSU only that you will store a Boolean array. Bool has cycle. Okay, has cycle, and when you are joining two nodes which have the like which are in the same component, then you will just do has cycle equal to true. So you can just for every edge in the input, like for every pair of numbers in the input, you will just add one edge. You will just add one edge between those two components, and you will just update the DSU. And finally, you will just iterate over all the components in the DSU and check if they have cycle or not. So if they have a cycle, then you will just increment the answer by the size of the component. And if they don't have a cycle, then increment the answer by size plus one and minus the number of self loops. And that's the final answer. Okay. So this was pretty good question. Like if you have not if you have not seen this concept, then it is pretty like it is pretty tough to get it. So like I'll just show you that how I did this problem. Like which problems have I done before this similar to this. Okay. So you can solve them as well. So here this problem on CF, this problem is pretty similar to my problem. Like this problem has the same concept which was used right here. So I did this one, and it is of rating of 2100, by the way, 2100. Okay. And also I have done this problem which came in the recent contest of Div 1, recent Div 1 contest, um, where I solved two problems. Yeah, this one, I think. This one. So this problem is also having the same concept of the graph, right? And this is rating 2300. Okay. And one more problem that came, it was in ICPC Madras, ICPC Madras Regional 2024. In that, the problem I think, or problem L, it was also the similar concept. Okay. So because I had done these three problems, the idea struck me very fast. And you can just do this. So I'll just show the code now. And if you did not really get a solution, then don't be disappointed. Just try these problems first. Like if you are comfortable in solving the rated problems having rating more than 2000, then just try to solve this problem and that one which I told you, baggage claim, right? And then you will probably be able to solve this problem. All right. So I'll just show the code for this. It is pretty elegant. So we have the input LLN, CNN, and I just make the DSU arrays, parent and size, and also this has cycle, right? Initialize it to false and the size to 1 and the parent of I equal to I. Then I have these join and find and join functions. So for find, it is normal DSU find function. And for join, if in join, I am updating cycle as well. Like if I want to join A and B, I'll first do A equal to find of A and B equal to find of B. If A equal to B, that means they're in the same component. Then I am trying to add an edge in the same component. So has cycle of A will become true and I'll return, right? And then if they're in different components, then SI if SI of A is less than SI of B, then swap AB. This is just for small to large merging. Like it is optimization that if you want to merge A and B, then just merge the smaller one into the larger one, right? So I did that right here. And if uh, A and B, like if A or if B initially had cycles before joining, then after joining also that component will have cycle. So if a B has cycle, then I'll update has cycle of A to true. And if A has cycle, then it already is true, right? And Si of A plus equals Si of B and parent of B equal to A. So this is my join function. And here I have this vector of bool called self. So self means that self of I will be true if the node I has a self loop. Okay. So int AB, C in AB, then zero indexing I did. If A equal to B, then self of A equals to true. And also I join AB. Then ans equal to 0. Now I'm just iterating over all the components. So if parent of I is not equal to I, then it is not a component. So I'll continue. And if has cycle of I, that means if the current component has a cycle, then ans plus equals to the size of I. Otherwise, the ans plus equals to size of I plus 1. Okay. And I'll just print this thing minus the number of nodes which have a self loop. So I just print the sum of this self array. Ans minus sum of the self array. Okay. So actually this problem was pretty good, to be honest. Like on CF at least 2200, I guess 22 or 2300. But because of cheating, many people solved this. Like as you can see in division 2, this problem E was solved by many people. 200 people is definitely very large, because in div 1 there is minimal cheating. Okay. And in div 1 uh, only 100 people would solve. So it makes no sense that in div 2 more than twice, I mean approximately twice the number of people solved it. Right. So it was a pretty nice problem actually. So yeah, that was solution. And like if you have any doubts, then like if you have some doubts that is in the approach, then you can ask me right now. And like if you didn't get it at all, then you can just try those two problems which I told you. Okay, so you are 1100 rating, then definitely you should not try this problem. But yeah, thanks for staying till the end. I mean, if you knew that you do not could not solve this problem, but still you are till the end. So thanks for that. You got first fourth question. First four questions. Yeah, that's nice. That's good for your rating. That like probably you it will increase if you keep it up. In contest, you got first four questions. All right. So that's also not in contest. Okay, you got the first four questions now, right? Yeah. So that's nice. That's fine. And okay, so for the YouTube, like if anyone has a doubt, then you can comment on the YouTube video, and I'll reply. And for the last problem, if you did not get my solution, then I highly recommend you to solve these two problems. One problem is this baggage claim code forces, and the other one is desk disorder code forces. Right? So these problems you can try. And after that, you will try this problem, and definitely you will be able to understand my solution. So, anyways, let us just end this PCD now. Uh, Thanks for joining. Okay, you are solving level 4 TLE course, but finding deep problems too difficult. 3DP. Well, if you know the theory and if you have done the basic questions and if you are able to solve them, then it is just about the practice. Like, how much are you practicing the hard ones? So as you practice the hard ones more, you can solve them. And like at the rating of 1100, 1200, DP doesn't even come, right? So even if you know basic DP, then it is fine. Okay, until your rating increases. All right. So anyways, I'll just end this meet. All right. So bye. Bye guys. Good night. So how do I end the meeting? Okay.